Hi, good morning. I had hoped on the Sunday morning after the gala dinner that everyone would be nicely snoozing away while we gave the presentation. I can see from the question and answer session that we've just had that due to the resilience of divers that you're all here, you're all awake, and we've actually got to pay attention doing this. What we're going to do is present you basically two views on pre-market testing of diving rebreathers. And with that, it'll be a transatlantic view. I'm obviously standing here as a Brit and a European, and the role that I and Kinetic fulfill is very similar to that of NEDU in the States for the US Navy. We provide a similar role for the Royal Navy. So we're an independent test house. We don't manufacture from that point of view. Mike is going to present his view on this very much from a manufacturer's perspective. What I'm not going to do today, and we're not planning to do today, is to teach you how to actually determine the work of breathing, how to determine the canister endurance, and exactly how to do the testing. I want to cover a slightly more higher view of pre-market testing, of what it's about and where it comes from. What I'd like to do is to start with some diving safety considerations from pre-market testing. We're all here. Rebreathers have been used for a long time. They have been successfully used for a range of diving activities. I think we all know that it's stemmed from the military, and the military are very much using them. The commercial world are using rebreathers, and I mention this in the generic sense because looking at the presentations so far, there's one complete part of the diving industry that's got hundreds of thousands of hours of rebreathers underwater that haven't been mentioned. The saturation divers in the North Sea, the Norwegian sector, it is compulsory for them to use a bailout rebreather. So every dive at a certain depth, they are using a bailout rebreather, and there's hundreds of thousands of hours there. And we know about recreational, technical, etc. So they are successfully out there for a range of activities. But we all know with diving there are inherent risks. As soon as you go underwater, there are risks of undertaking diving activities. And as divers, we're all prepared to accept those. I think the big thing with rebreathers is these risks can be very much exacerbated by rebreathers. They can be very simple or very complex. I think in recent years, with electronics, etc., we are seeing much more complex systems. And with these, there can be an insidious outcome, and they can lead to incidents. I mean, hypoxia, hyperoxia, hypercapnia, we've heard all those, but it can be insidious. We've also seen over the last couple of days, history shows that there are too many incidents. And whatever we do, and as a group I think we have to lead on this, we need to reduce the incidents. And it's a responsibility of the whole industry to improve diver safety. And so with pre-market testing, what I'm going to cover, it's the whole industry is responsible for that part of diver safety. So if we're going to define rebreather performance, what are we actually looking at to try and define the performance? Well, this is a phrase I'm likely to use several times during this. We need to ensure that rebreathers are fit for purpose to do the job that we wish them to do. And really, when we go diving, we are going into a hazardous, extreme environment. We can't breathe water, so we have to be provided with something to breathe. It can be very cold. So what we need this respiratory equipment to do is to protect us from drowning, allow us to breathe, and do what we want to go down there to do. To move about, to work, to enjoy it, to take photographs. And that's what it's got to protect us from, to be able to do. Now, it's protecting us from that environment, the fact that we're underwater and it's cold. But the apparatus has to protect us from itself, its own inherent hazards. We all know about the 3 H's. I mean, I've got an illustration there of Floyce with his first rebreather. I mean, he removed the CO2 by soaking rope in caustic soda. You know, that's an incredible risk to put that in there. So we need to make sure that it protects us against itself. And another phrase that will come up, in doing that protection and reducing the risks, we have to invoke the logic of a LARP as low as is reasonably practical. And many people ask me, what does this really mean? Well, it's looking at a pragmatic and a cost-effective way of providing that protection. And specifically with pre-market testing, looking at the cost and timescales and intricacy of doing that. You could test every possible parameter. It could take tens of millions of dollars or pounds, but is that reasonably practical for the industry? But one thing you need to do to define is you need validation testing, and we've heard that it needs to be independent validation testing. I'm not a manufacturer, but I talk to many manufacturers about diving apparatus and the whole concept of testing, and they all have a very similar view on this. The manufacturers out there want to sell you and provide you with a safe product. I haven't met any manufacturer who wants to sell you something that's deliberately going to be dangerous. So they want to give you a quality product. And there's several reasons. One of the things is to reduce the liability. But if they've got a safer product, reliable, they get a greater market share. So there is a driving factor for all the manufacturers. But from their perspective, it's got to be commercially viable. So when looking at what's testing that we do, we only need to specify and test what is actually required. There's no point. Dan Warkander sort of said that you could do days and days and days of endurance testing. Do you actually need all that to provide information that is practical to move forward? So only specify and test what's really required. Hence the 4 degrees moderate work rate on canisters to reduce the time. Plus, test equipment is expensive. Many manufacturers have invested heavily in test equipment. You've got to look at how much they have to invest compared to the returns. The other thing is, what do you use this testing for? Well, all manufacturers test their equipment during the product development. There's nobody who puts it together and then walks along and says, that is it. So during production testing, lots and lots of testing goes on, or production development. And then after that, you get 2 types of certification, really. One is type testing. Once the manufacturer has got a piece of equipment that they think, right, this is what I want to take to market, he will then put it through a formal series of tests, type testing, usually with independent audit and certification, to show that that design will work. The other aspect is, if he is going to make thousands of these, then he has to have a production quality test. It's no good the very first one being okay and then the rest slowly degrading as they make them. So there is quality control testing as well during the whole pre-market aspect. The unfortunate one as well is manufacturers can use testing for complaints and investigation. If they have got good baseline data and then somebody comes back to them with an apparatus and they test it and say it's exactly as it should be, then it's useful for them for that. So some of the testing principles that we look at. Conventional engineering. We're taking these equipment into a pretty harsh environment. Got to make sure that the mechanical strengths are right, the connections are strength, that it's just well engineered. Also the testing, particularly from a performance need point of view, needs to be physiologically based. It needs to understand the physiological aspects that you're trying to support and verify. There's no point doing testing on a breathing circuit, the performance of that, if it has no relevance to the person who's going to be breathing at the end of the day. And that physiological-based testing can come in several ways. Unmanned testing, you know about canister endurance for CO2, worker breathing. It can be extensive man testing. The picture bottom right is of one of our little test pools. It's 120 meters by 60 meters by 5.5 meters. But you know, it's putting men in the water there. And ergonomics, form, fit and function. You can make a perfect rebreather from a breathing point of view that's impossible to wear virtually. You can't reach the controls. When developing testing, I said a while ago, it's the whole industry who are responsible for this. And what testing required is a consensus. And we'll come back to consensus when we talk of standards. That consensus includes technical experts, your engineers, your physiologists, looking at, you know, leading edge and appropriate best practice in those. It includes the manufacturers from their perspective. You know, what to build, how to build it, what can they sell. Test houses, accreditation agencies. You know, it's no point in putting together testing principles if test houses aren't able to follow it. And also with that, with users. What information and data do you want? What do you need to know? You need to know your canister endurance, what depth you can use, what gases. So there's a user input to all this. But within that, it's got to be technically possible. There is no point in writing tests, and I'm afraid some of us have been there and this has happened, that can't be done. It's got to be something that the manufacturer can run through one way or another, and any testing authority can complete. And I come back to that. It's got to be a LARP. It's got to be cost effective. It can't cost $10 million for something that you're only going to sell for a couple of $1,000. So what do we need to specify and validate and test? Well, I've mentioned mechanical engineering. I'm not going to cover every detail. It's the principles. But if you've got hoses on there, are they fit for the pressure? Will they bend correctly? Pressure connections, are they right? Are your pressure gauges right? The materials that you use, most people are going to take them into seawater. Are they going to corrode if you've got dissimilar metals? High oxygen levels. Is it going to be compatible with high oxygen? Testing and that. Biological. Will it actually just rot away? Will it degrade? Are the materials such that when you put this in your mouth, you will get allergic reactions? We all know about breathing performance. We need to get the breathing performance right. The work of breathing, respiratory pressures, elastance. This is one that has been challenging us for years. And I'm not going to go into huge detail here of what levels we look at. But we are constantly looking at the best physiology and what is relevant. I mean, the current version of the European standard uses something called peak-to-end respiratory pressures. It's a double accounting system. It's wrong. You know, we're starting to look at elastance to overcome that. Inspired CO2. We've had many talks on that and the need to specify what levels are acceptable. And what is interesting, you know, are we going to have to start looking at end-tidal CO2? What numbers are relevant? That's one of my big concerns with that one. There's a huge variation, and you may set a level where some divers will never get in the water. We've just had a talk on PO2 control. What should the control be? Looking at that. Gas and absorber endurances. How's this going to perform in the tropics and the cold areas? Hot and cold. I mean, there are user groups who take this, you know, into the Arctic Circle under ice. You know, these things are frozen when they start to put them on and fit them. The materials have got to cope with that. The other side, hot. I've actually seen in recent years, the last couple of years, on the deck on the ship in the Gulf, temperatures can be 55 degrees. All your rubber components go all soft and floppy. and helium can penetrate through those. So you've got to look at those extremes. And the extremes subsurface. For instance, canister and sensor performance in cold and hot conditions. This is one that's easy to forget. Some of the user aspects. Marking the equipment, giving information to the user, labeling it. What labeling do we put on? We have discussed so far checklists. That is a user aspect. You know, should there be a big, almost sticker over the mouthpiece that you have to tear off that says, have you done your checklist? Which you have to take off before you can put it in your mouth. You know, how do you label it? How do you give instructions for use? One interesting sort of aspect on this, and we'll come to that, to prove that something has been pre-market tested and validated, the European standard requires certain marking. You will see that there is a CE mark. It will tell you which standard it's marked to, and also who certified it. So if you've got doubts on that. And a little bit tongue-in-cheek at this moment, I'm completely against paper-only checklists. If you've ever tried to use a paper-only checklist on a dive boat in England where it's always raining, it won't work. You've got to laminate them. Ergonomic, form, fit, and function. You've got to test that diver controls, the divers can reach them, they can operate them, they can find them. The displays, you can see, they give you warnings. There's a little example there of a configuration of a set where one of the hoses went right over the weight release. So if you tried to get it, you couldn't release the weight. And a big one, functional safety. Safety critical systems we've talked about. That is a requirement and a specification. Just looking at functional safety, certainly the European standards call up failure mode effect and criticality analysis as an essential part of rebreather safety. Where we've probably made a mistake is we've said you must do this, but we haven't said what level of risk or failure or criticality is acceptable. And you need to quantify it. And hopefully, it's fingers crossed because it's still going through the mill, we found a way of quantifying the FMICA for rebreathers to give guidance as to what is acceptable. And just as an example of this, many of you have probably come across this type of risk matrix. What you get is, if you look at the column on the right-hand side, what is the severity of the outcome? So that could be what is designed or defined as catastrophic. That's where several people may die. If the cylinder on a dive boat goes bang, then it's possible that several people may die. You can get to the other end of negligible, that if you go to turn a handle and it breaks off in your hand, you may rip your knuckles open. You know, it's not life-threatening. But then you look at the likelihood of this occurring. Is something going to happen frequently? You know, if you're likely to cut your finger on it every other dive, well then it may be negligible, but you look at the probability and that can become an unacceptable risk. But to calibrate this type of approach, and one thing I'd like to identify, this is the likelihood of a dangerous failure of a safety critical part of the system for one rebreather's typical use for 1 year. And we're looking at, and this is how to sort of calibrate this matrix, a critical event is defined as a single fatality. So if we're looking at a single fatality for one rebreather for a year, then what is typically acceptable is that this is very unlikely to occur, less than 1 in 10,000 to 1 in 100,000. And so that is considered about the level of acceptable risk. And so this calibrates this approach. And this will be the logic, we hope, for looking at functional safety for rebreathers in the future. talk now more about specific standards. I think a lot of people, I seem to have got labelled as the person on standards. I forget everything else that I do, but there are many standards out there. And looking at the history, from my knowledge, the first sort of international standard started as an agreement between the US Navy and the Royal Navy in about 1978, 1979, the B-12 agreement. That was the first time that we defined you will test worker breathing, etc. That followed on over in the UK to sort out fatalities in the North Sea with the Department of Energy and Norwegian Petroleum Directorate guidelines, first in '84 and then followed up in '91. That's actually developed further with the Norwegian sector taking that on. The current version of that standard is 1999, and I know they're going through revision of that. NEDU, tremendous amount of work over the years. I mentioned the IAP B12, where a lot of it came from NEDU. Their technical reports, 194 up to 2010, defining the requirements. Linking it all together, I have the interesting challenge of trying to get multiple nations in NATO to agree on something. And there is a NATO STANAG which introduces the latest thinking, and it probably has the latest thinking on breathing performance standards, and I've worked with Dan Wakanda very much on that. But you come to a standard which has been mentioned time and time again over the last couple of days, EN 14143, the European Standard for Diving Rebreathing Apparatus. What makes this standard particularly unique compared to all the other standards define the respiratory aspects, what the worker breathing should be and the CO2 levels. What they don't do is they don't standardize the whole apparatus and how it fits and how you should use it. And that's what makes 14143 unique as a standard. Now, I don't know if this is Daniel into the lion's den, but as a Brit, or more importantly, as a European standing up here, de facto, is EN 14143 now the world standard for diving rebreathers? We have people in this room from many nations, North and South Hemisphere, and we're all talking about that standard. Is this now the standard? What that standard does is it does cover all these aspects, but then pulls in many other standards as well. So if you have an open circuit bailout, it will link to EN 250 for the open circuit side. If you have a buoyancy compensator or a wing, it links to the standard for those. It links to the connections. I mean, a very simple thing is, what connection on your cylinders. It's standardized, and you can move around the world and use them. And it also calls up functional safety standards, and there's a range of ways of doing that. What I want to do is to just try and help you with trying to understand where the European standard comes from and how it fits into it, and the European PPE directive. PPE is personal protective equipment, and within Europe, this is effectively European law. A directive was issued in 1989 to say, really, that systems have to be fit for purpose. It's been amended since then several times, but it does say that rebreathers, as PPE, have to be fit for purpose. That's all fully understood. Now, just to talk about the bureaucrats, within the PPE directive, and this is how much the bureaucrats know about diving, is diving apparatus has to protect the diver from pressure. So you can imagine what we're up against as far as bureaucracy. Rebreathers have to be fit for purpose. Diving rebreathers are what are called Category 3 PPE. What that means is they have to be type approved. So you have to prove before you start going onto the market that it meets the requirements. It has to have through-life certification testing. That's called Article 10 and Article 11 if you want to be ANAREC. And it has to be certified by a notified body. Two ways to achieve the CE certification. One, actually, you have to do it either way. You have to produce a technical file. You have to produce, really, a collection of documents which tells you what the design is and what all the performance is. And where possible, you have to test and approve to a harmonized standard. A harmonized standard, such as EN 14143, means that it complies with the directive. And so that is harmonized for rebreathers. Where and who should test? Well, I've mentioned development. The manufacturer should test in-house, and you can use specialist test centers. Before pre-market release, it has to be overseen by an independent authority, this notified body. Now that can be independent witness tests in-house at a manufacturer, or it can be an independent testing. Who is competent? And this is really a big one for debate, and I'm not going to try and defend this. The notified body is appointed by the individual nations within the PPE, and they should check that the notified body is competent to do this. But it should also be a competent test house. Now, ideally, they'd be formally credited, but actually, trying to find a test house with formal accreditation for diving rebreathers is almost impossible. As far as I know, there's none. I don't know what the Swedes' accreditation is, but it's too expensive for most test houses to get formal accreditation. But a test house does need the appropriate facilities and expertise. It's no good buying a breathing simulator if you don't know what to do with it and what the numbers mean. And it's a little bit unfortunate that test house competence almost comes from grandfather rights. I mean, NEDU and ourselves at Kinetic have been doing this 30, 40 years. And I suppose in many ways we have taught a lot of other people from that. So, just quickly looking, because the time is nearly up for me on this, EN 14143 is an international consensus standard. It's not ultimate. It will always be wrong, but it's the best that we can all agree on at the time. Some people have more comprehensive assessments, and particularly when it comes to manned performance and ergonomics. It is a harmonized standard. There are over 50 separate requirements and tests in there. It's a huge amount of testing, and it's a huge burden on the manufacturers. And the testing covers pragmatic aspects of the physiology, the mechanical aspects, functional safety, and the user aspects. It is constantly being revised. And I come back to this word, it's a whole industry consensus. So when you look at the standard and say, why did they do that? It's because everyone has tried to agree on it. Okay, I had put for questions at this stage, but I think looking at the time, the best thing is really to hand over to Mike now and let Mike do his part, and we'll pick up any questions at the end.